Okay, so this is the outline of chapter 21. So we'll talk about the Coulomb's law. So Coulomb's law, how the charged particle will interact with each other. There will be force acting on them, either attracting or repelling them. And then we'll talk about the charges quantized, charges concept. So this is not, so just a small introduction about these two terms. So you feel it's quite bored, in my opinion. Okay, so first, we have let us start from some tiny experiment. Okay, so the title is called magic. Okay. So here it says we have two glass rods. Okay, from this figure we have two glass rods. Okay, we're each rubbed with a steel cloth. Actually, you don't really need to remember this detail. Just just like hearing a story is fine. I will not ask you in the quiz or exam. Okay, so here we have two glass rods and then rubbed with steel cloth. And then one was supplanted by thread. When they are close to each other, they repel each other. Okay, so here, this one, we hang this glass rod here. Okay, so this glass rod is free to rotate. And then we try to rub this side and also rub this side. So in this case, let me see. So in this case, okay, so they will repel each other, which means that there will be force acting on this rod and also this rod. So this side will, there will be a force acting on this glass rod to the top left, and then another force acting on the bottom rod to the bottom right. Okay, so due to the Newton law of motion, there will be two forces acting on opposite direction with the same magnitude. Okay, so this is the first experiment. So so it asks whether it's magic because there are some force repelling them. And then the second setup, we try to change something. So the bottom glass rod is the same, so it's still hanging there, so it is free to move. And then we try to change the second glass rod into a plastic rod. So the plastic rod was rubbed with fur. Okay. Also, you don't need to remember the material. Okay. So here, when brought close to the glass rod, the rod attract each other. So the phenomenon is different from the bottom one. Okay. If both of them are glass, they repel each other. And then for the second setup, okay, here we have the plastic rod, and then they will attract each other. They will attract each other. So we can find something worth to discuss from a physics point of view. Okay, so of course this is a physics class. This is of course not a magic. So we need to find something to explain this. And of course, in the past, the physician tried to use something called a theory. They should try to build up some theory to explain the phenomenon. And then, as much as the theory do not contradict with each other, then the theory is good. Otherwise, the theory will be abandoned. So let's try to explain this phenomenon. Here we will consider, okay, after rubbing the glass rod, we will have positive charge. We will have positive charge on the glass rod. So don't ask why we have positive charge. Of course, it is related to the chemical things, or how many electrons are at the outer sphere, something like that. Okay, so so as much as they have the same charge, same sign of charges, on the rod, then they will repel each other. And for the second setup, okay, it's the upper one is still the glass rod, so it still have a positive charge. But for the plastic rod, okay, we'll assume it will have a negative charge. So these two rods have opposite sign of charges, so they will attract each other rather than the bottom case as repelling each other. So that's the explanation for these two setup. Okay, so here it says plus sign indicate a negative charge and minus sign indicate a negative charge. So the quick conclusion is that the particle with the same sign of electric charge repel each other, and particles with opposite sign attract each other. Okay, so here in this slide, we will slightly talk about in the world we have separate the material into 4 types in terms of conducting ability. Okay, so here it says a material classified based on the ability to move charge. To move charge, to move charge means whether the to move charge, I would say the conducting ability. Conducting ability. In Chinese, it is called 导电性能. 导电性. Oh, whether any free electron can be moved on this material. So roughly, we have 4 types of material. The first one is called the conductor or 导体, a material in which a significant number of electrons are free to move. So example includes metals. So yeah. So in the periodic table, conductors are mainly on the left side, and also the 2B, 2A and 2B are mainly the metals. And then the second type is called the insulator or non-conductors. So the charged particle in non-conductors, okay, or insulator is called JUNT. Are not free to move. Examples include rubbers, plastic, glass. Okay, so mainly on the right side or some compound or some composite component. Yeah. Okay. So or some organic stuff, plastic, something like the organic stuff. Glass is also. Okay, so it is somehow like the primary science class. Yeah, we have a conductor, insulator, and yeah, for the third type, it is called a semiconductor, 半导体. So in the periodic table, it is mainly lie in the middle part, or around the 4A, around the 4A, 5A. Some of the elements are semiconductors, like silicon, germanium, something like that. Of course, in this class, we will not focus on the semiconductor. For ECE students, they will have class like applied electronic or microelectronic class about the semiconductors. Why? Because it is very difficult to calculate. So they need to spend a whole semester to talk about or more than one semester to talk about the semiconductor material. And that's why in high school chemistry class, when we talk about the semiconductor, yeah, they'll just introduce you, this is this element is the semiconductor, and then we stop. They will not go deep into it because the physics in the semiconductor is very, very difficult. Yeah, so in the physics, if you really want to go deep, something called the solid state physics. Sorry, solid state physics. 固态物理 is about the semiconductor. We will need to use something like quantum mechanics to really explain what is the phenomenon inside the semiconductor. Okay, but of course, in the nowadays, many chips need the semiconductor, like CPU or the chip on your mobile phone, whatever. So the chip we need the semiconductor. So yeah, and the final one is the superconductor, 超导体. Okay, maybe this one you may not have heard it in primary or high school, but yeah, maybe you may heard of this name before. But yeah, this is a very special types of material which has which are perfect conductors, which means that for conductors, for normal conductors, there will be resistance, 电阻 resistance, 电阻. Okay, even for some good conductor like copper, silver, gold, this kind of good conductors, they still have a resistance. But for superconductor, the resistance inside it is perfectly zero. Okay, but of course, to achieve the semiconductors condition, it is not easy at all. When the physician try to discover, when the physician discover the superconductor, they need the liquid helium. Liquid helium, 液态氦. So the liquid helium can be go as low as like 4K, 绝对4度. Okay, so it's around negative 269 degrees Celsius. Okay, as close as this one. Okay, so yeah, or it really need as low as around hundreds of more than 1K to really achieve the superconductor at the very beginning. Okay, so yeah, it's not easy to achieve, but yeah, so they call 高温超导 because it really needs some really low temperature, and then the chemistry or material engineer try to discover some of the material can achieve the superconductor for higher and higher temperature. Okay, so these are basically 4 types of material based on the conducting ability. Actually, for this course, we will mainly talk about these 2. Yeah, for electrostatics. Yeah, most of them. Yeah, most of the point you need to notice is whether the material is conducting or non-conducting. There will be 2 types of a phenomenon. Yeah, for the conductor, there will be no charge inside. The charge will go to the outside surface. For the inductor, for the insulator, there will be no free electron. As this said, the electron inside it are not free to move, so it can have a fixed charge distribution, and then you need to calculate what is the E field generated by it, something like that. So up till now, you only know you only need to know there are something called conductor and then something called insulator, then it will be good enough. Okay, so yeah, so here it says the charged particles. So yeah, charged particles. Okay, so when you learn the chemistry, you know, for an atom, 原子, okay, it is constructed by 3 types of smaller particle. One is called protons, one is called neutrons, and also another one called electrons. Okay, protons is 质子, and then neutron is 中子, and then electron is 电子. Okay, so in high school chemistry, you should have know 质子、中子、电子 already. Okay, so and of course, as you know, the protons have a positive charge. The proton has positive charge. The electron have negative charge. And then for the neutron, it is electrically neutral, no charges at all. And then, of course, for a normal atoms, okay, the number of protons should be the same number of electrons. So the total charge of a normal atom should be also 0. Okay, so yeah. And then as you know, the protons and neutrons are packed tightly together in the central nucleus. So it is something like there will be a positive nucleus, and then there will be some electron rotating around it. Okay, so there are some proton, and then also with some neutron, something like. Of course, this is not alike as this one, just demonstrate inside the nucleus there will be protons and neutrons, and then for the for the electrons they will just rotating around, not necessarily a circular sphere or circular orbit. Yeah, maybe there will be something like 1s 1s2 2s2 2p6, something like that. I expect you have learned it in chemistry, but you don't really need that kind of knowledge in this course. Okay, so yeah, so this is the charged particles. Yeah. And of course, in chemistry class, you also know something called the ions, 离子. Okay, so if the atoms lose a electron or lose multiple electrons, then it become positive ions. If if an atom can gain some or gain one or more than one electron, then it will become negative ions. Okay. Of course, usually for metal, usually they are on the left part of the periodic table, so they tend to lose electron, because for the outside sphere or the outside orbit, then it will have something like 1 electron, 2 electron, 3 electrons. So they will tend to lose the outer electron to become a positive ions. Okay, so yeah, so here it says the induced charge. So here this is the setup. Okay, we have a neutral copper here. So of course copper is a conductor, and then neutral means the total charge. The total charge on this copper rod is 0. Okay, we do not expect there are some charge going on it or going from it. So total charge should be 0, and then we just hang it here, and then just as the second setting in before, we have the charged plastic. We try to rub it with a bird, so it has a negative charge on it. And then if we try to place this charged plastic wad close to the neutral copper, there will be something called induced charge, 感应电荷, 感应电荷, induced charge. So it doesn't mean it generates some charge there. It just try to, some charges just move away. Some electrons just move away from there, because this is positive, this is negative charge, and this is non-conductor, this is insulator. So this kind of negative charge are not free to move, they just stay there. But here, this is a plastic rod, this is a, sorry, I mean this is a copper rod, this is a conductor. So the electron on it are free to move. So this negative charge will be repelled by this plastic rod on the negative charge on the plastic rod. So it go to the other side. And then as much as the negative charge go to the other end, so this end will be positive charge, will induce a positive charge. And this side will have a negative charge. Of course, still, although the charge are not so uniform, but the total charge is still 0 because there are no charge going in or going out. But the case is that as much as the negative charge go to the other side, this side becomes positive charge, and then this side is a negative charge. So these two rods will attract each other. So this is the phenomenon for the first setup. Okay, so is that here the conducting electron in the copper rod are repelled to the far end of the rod by the negative charge on the plastic rod. Then that negative charge attracts the remaining positive charge on the near end of the copper rod, rotating the copper rod to bring that near end closer to the plastic rod. So up till now, yeah, the physician tried to explain these three phenomenon using the concept of positive and negative charge. And based on it, it just assumed that if the charge has the same sign, sorry. Okay, so if the charge has the same size, they will just repel each other. 它会排斥，同性会排斥。If the charge are in opposite sign, they will just attract each other. Okay, sorry. Yeah. Okay, so yeah. So yeah, so this is pretty much I did. Okay, so yeah, throughout this semester, or at least in this few weeks, if you have questions, just feel free to ask on the chat room. Chinese or English are also okay. So if I recognize it, then I will try to answer your question. So don't be too shy if you don't really understand. Actually, if you just require me to explain something in Chinese again, or then it will be also okay. If you really ask, if you don't ask, then I will just keep moving forward. Okay, so up till now, if no question, I'll just move on. So here is a bachelor level of physics course. We can not only talk about the phenomenon only. We need to have some mathematics. So we have some definition. So first of all is the charges. It's the charge. Okay, usually for the charge, we will denote it as Q. Charge is Q. Okay, Q. And then if we try to take the derivative of the charge with respect to time, then this variable is called the current. The current. Okay, current is 电流. Okay, charge is 电荷. Okay, which means that if some of the charges move, then there will be current, which means that if dq is changed, the charge amount is changed in a unit time, then there will be so-called current. And of course, this is a physics course. Try to remember all the SI unit. SI unit is very important. Yeah, during the quiz or exam, for every answer, you need to write the correct SI unit. If you cannot write the correct SI unit, each one will worth 1 point. So yeah, so try to keep in mind what is the SI unit. In physics, engineering, SI unit is very, very, very important. Okay, so for the charge, SI unit, the SI unit for the charge is Coulomb. Coulomb. Okay, so yeah, in this chapter is called Coulomb's law. Okay, so the unit of the charge is named after him. So Coulomb, and in short form is C. Okay, so yeah, so based on this equation, okay, you can see that for the SI unit of the current, it should be ampere. Ampere. Okay, in short form is A. Okay, so usually when we just try to plug in all the SI unit in the equation, it should be correct. So I is A, and then dq d in the denominator and the numerator both have d, so we don't need to care about dd. Yeah, because when you learn calculus, d means delta, so just change of charge and change of time. So d don't have any SI unit there. So dq should have a SI unit of c, the Coulomb. And then for the time, SI unit should of course be the second s, small s. Okay, so we have A equals C over S, or A is like A equals C S inverse, something like that. Or if we just move it to the other side, C is AS, A times S. So 1C is 1A times 1S. Okay, so this is the definition of the charges, of the charge. Okay, so here is the main part of the Coulomb's law, but yeah, of course, you should have learned it in high school physics, I think. Okay, but anyway, I will still talk about it. Okay, so here it says the Coulomb's law describes the electrostatic force between two charged particles. Two charged particles is the main keyword in the Coulomb's law. So as much as we have two charged particles, then we can quantify the electrostatic force. Electrostatic force, okay, in Chinese it's called 静电力. 静电力. Okay, there will be force acting on the charged particles. Okay, the force can be either attracting these two charged particles or repelling these two charged particles. Okay, so Coulomb's law describes the electrostatic force between two charged particles. If the particles have a charge, Q1 and Q2 are separated by distance R and are at rest or moving only slowly relative to each other. Okay, so this is called 静电学啊，静电学或者静电力啊。Okay, or we will say electrostatics. Electrostatics 啊，静电学。So for this statics, 静, it means that we assume everything doesn't move at all or move very slowly. So we will assume that these two charges are at rest or moving very only slowly relative to each other. Then the magnitude of the force acting on the charged particle will be given by this equation. by this equation. Okay, of course, the force will be just true for that moment, because as much as you know the Newton's second law of motion, which means F equals ma. So as much as there will be a force acting on a particle, then yeah, if this force is divided by the mass, then there will be the acceleration on the particle. Then for the next moment, it will just move. When it moves, then the distance will change. So that's why we need to mention it is called electrostatics, or this force is called electrostatic force. This force is only true for that moment. We assume all the charged particles are just at rest at that point, okay? And then you can only calculate the correct force at that moment only. Later on, the force will change because there will be force acting on them, and then they will try to move, so the distance will change. Okay, so yeah, so of course this I think you should have learned it before. But yeah, there will be some tiny thing maybe you don't know yet. We will use this kind of notation. I will talk about it later. So before talking about this equation, yeah, there are something called the permittivity constant. The permittivity constant. Yeah. So which means this epsilon naught. Okay, this number is 8.85 times 10 to minus 12, and then with a complicated SI unit. Of course, you don't really need to remember. Basically, I think in the quiz, I will just provide it to you. Or usually, we will just use the whole thing. The whole thing K equals 1 over 4 pi epsilon naught. Okay, which means that usually this whole term will just appear together. So yeah, so many of the times we can just use K. This is the big K. This is the K, not big K. This is the K, and then the number is 8.99 times 10 to the 9th power Newton meter square, and then over Coulomb square. Okay, so that's the constant, the constant variable in the Coulomb's law. Okay, so for the epsilon naught, it is called 导电率，电导率啊，电导率。Yeah, actually the Chinese name is not too important in my opinion. Okay, but anyway, yeah, we will have permittivity constant for the electrostatics, and later on when we learn about magnetism, we will have another variable called mu naught, which is the permeability constant when we learn this one in chapter 28. I'm not sure, chapter 28 or chapter 29, which is around there. Okay, so yeah, 电导率. Okay, so next we will talk about this equation. Okay, so here, if we try to write this Coulomb's law in the scalar form, it will be as simple as F equals 1 over 4 pi epsilon naught times Q1, Q2 over R squared. Okay, so there won't be this thing and also this vector sign, and also this so-called unit vector. Okay, so this R hat is so-called unit vector in our axis.凹轴的单位向量。Yeah. Okay, so here it means that when we talk about the force acting on Q1, here we have two charged particles, Q1 and Q2. Okay, so here when we talk about the force acting on Q1, then we will have the R-axis starting from Q2 and then point to the right side, point to the right side. Starting from here, point to the right side is for Q1. Q1. So this is the R-axis for Q1. Okay, and then R hat is the unit vector, point to the R-axis for Q1. So here we have R hat. Okay, so here, if both Q1 and Q2 are positive, if we try to plug it into here, so Q1, Q2 are positive number. Also, R square is a positive number. Okay, so the whole term Q1, sorry. Okay, so let's see. We have Q1, Q2, Q1, Q2. Okay, if both of them are right like this, Q1, Q2. If both of them are positive number, so of course R square always be a positive number, unless R is 0. But yeah, we can't have R equals to 0. There must be some separation between them. Okay, so in this case, Q1, or I should say K times Q1, Q2 over R square is also positive. It's also positive because K is a positive number. K is a positive number. If Q1, Q2 are positive, R square is also positive, then this thing is positive. Then which means that F should have the same direction as R hat, which means that here, R hat points to the right side, and so as F. But when we talk about the force acting on Q2, here, we will define the R-axis in the other way around. We will start from Q1 and then point to this side. This is the R-axis for Q2. In that case, R hat point to the bottom left. Of course, as much as R hat is a unit vector, which means that the length of it is 1. The length of a unit vector is 1. Okay, so this is a unit vector for Q2. If in this case still Q1 and Q2 are a positive number, still F is also yeah. So F should have the same direction. F should have the same direction as R hat, because this whole thing is a positive number. Okay, but if Q1 and Q2 are negative number, if Q1 and Q2 are negative number, okay, in that case, negative times negative is still positive. So the whole term is still positive. It's still positive, which means that in that case, F and R hat should have a same direction. Should point to the same direction. Same direction, which means that it is still this F and this F. This F and this F. Okay, so in that case, when we just look at this is a positive charge, this is a positive charge, the force will repel these two positive charge. If both of them are negative charge, the force points to the same direction, which means that the force still repelling these two negative charge. But if we have one positive charge and one negative charge, then this whole term will be negative. Or the other way around, if Q1 is negative, Q2 is positive, this whole term is negative, which means that F and R hat should point to the opposite direction. Opposite direction. So in that case, if just say if Q1 is positive, Q2 is negative. Okay, then maybe I just change another color, blue color. If a Q1 is positive, Q2 is negative, then now F should point to the opposite direction as our hat. So here we have F points to this way, F points to this way. In that case, these two charge with opposite side will just attract each other. Okay, so this is the implication of the Coulomb's law. So we need to care about the sign of the charge, whether it's positive or negative. And as much as you follow the vector notation, okay, how we define the r-axis, okay, r, this is for Q1, this r-axis is for Q2, and then if you just plug in the number with the correct polarity, and then yeah, the F and the R hat should be correct in any case. Okay, so yeah, I think this is pretty much yeah, pretty easy. Yeah. Okay, so it just tells you that if both of them are positive sign, both are positive charge, they will repel each other. If both are negative charge, they will also repel each other. And if one of it is positive, one of it is negative, they will just attract each other. Just follow the vector notation. Just follow the vector notation. So this is the point that you need to slightly care about. Okay, so up till now, Coulomb's law is about two charged particles. Okay, if we have more than two charged particles, how we should do? So here it says a multiple electrostatic force. So here it says if multiple electrostatic force acting on a particle, then the net force is the vector sum. It's the vector sum, not scalar sum of the individual force, of the individual forces. So I think in high school physics, you should know how to add several forces together. You need to decompose the force into like x-axis, y-axis component. And then you add all the x-axis component together, add all the y-axis component. So the final x-axis component and the y-axis component become the overall force. Yeah. So this is the scalar, the vector sum, not the scalar sum. Okay. So you should know. Yeah, adding vectors together might be a little bit troublesome. Yeah, but as I think you should already learn it in high school physics. So it means that if we have n charged particles, so when we try to consider the force acting on the first particle, then you need to calculate the individual force acting on F1 one by one, which means that suppose we have five charges. We have Q1, we have Q2, we have Q3, we have Q5, Q4, and then we have Q5. Okay, so we all together have 5 charges at all this point, at this moment. Okay, so here if we try to consider what is the total force acting on Q1, then we need to consider it one by one. So first of all, Q1 and Q2, as much as they have opposite side, they will attract each other. So this is F12, and then Q1, Q3, they are all positive. So this is F13, and then Q1, Q4, both of them are positive. Okay, so this one F14, and then Q1 and Q4 positive and negative, so they attract each other. So this is F15. Okay, so when you need to calculate the total force, then you need to decompose all the forces into like x-axis component, y-axis component, and add them together. Okay, so yeah, even for the quiz selected problem, it will be as much as 3 to 4 particles like that. Okay. Yeah, so here we will talk a theories called the shell theories. Yeah, actually, for at this moment, I cannot really tell you why it is correct. I cannot tell you why it is correct at this moment. Yeah, after learning the Gauss law in chapter 23, so which means that 2 chapters later, when we learn the Gauss law, yeah, we will come back to the shell theories, and then based on the Gauss law, I can explain why these 2 shell theories correct. But up till now, you can, I hope you can just accept they are correct. Okay, but actually in this shell theories, as much as it is plural, yeah, actually it has 2, shell theory 1 and shell theory 2. Okay, for shell theory 1, it says a charged particle outside a shell with a charge uniformly distributed. Uniformly distributed. This is a very important keyword. In Chinese, called 均匀分布. 均匀分布. Okay, uniformly distributed on its surface, is attract or repel as if the shell's charge were concentrated as a particle at its center. At this center. Okay, yeah. So it looks quite complicated. Let me try to explain what it really means. Okay. So it means that if we have a charged particle outside a shell with a uniform distribution. Okay, here we have a sphere. Okay, sphere, not a circle. It should be a 3D, but I cannot draw 3D. Okay, here if we assume that it has a uniform charge distribution, it can be either a positive charge or negative charge. Okay, so this is shell theory 1. Okay, just say if it has a positive charge, uniform distributed on the surface. Okay, if we have some positive charge, and then some distance away, we have just say we have a negative charge. Let's say this is negative Q, and then the total charge on the surface is plus Q. Okay, so here, if we really need to consider the charge acting on this negative charge and positive charge, okay, it might be quite complicated. It might be quite complicated because before we talk about if we have 2 charge, then they should follow the Coulomb's law. But here, as much as it is a sphere, which means that, let's say, this charge and this negative charge should have a distance. Let's say this is called R1. But for this one, the distance are different. Okay, so in this case, we need to reconsider okay, we need to try to separate all the charges into different part, and then we need to calculate all the charge one by one and then add them together. Okay, so all the distance are different. So, and actually we generally we need to do a surface integral in 2 dimensions. So it may be complicated, but this shell theory tells you that you can just assume that, okay, all the charge on the sphere are just concentrate on the center. So here, if this if this distance is let's say small r, then it will be actually the same as all the charge are distribute at the center plus q, and then still we have a negative q here, and then this distance is small r. Okay, then for this case, you should know how to calculate the force acting on them. Yeah, this is positive charge, this is negative charge. So these 2 forces should attract them. So the F should be 1/4 pi epsilon naught times Q, and then over R square, something like this. Okay, so yeah, and so as this one. So there will be the force acting on this sphere and also on this negative charge. This F should be actually the same as this one. So this is what shell theorem 1 tells you. And then let's see what is the shell theory 2. A charged particle inside a shell with a charge also uniformly distributed on the surface has no net force acting on it due to the shell. Has no acting on it due to the shell. So which means that it says shell theorem 2. Okay, so here if we have a charged particle, okay, a sphere with a charge uniform distributed, okay, let's say positive charge uniformly distributed on the surface. Yeah. Okay, so if positive q. So if we have a charge inside this sphere, let's say here, not necessarily in the center, at the center. Okay, not necessarily at the center. Just say here. Then this shell theory tells you that there will be no force acting on this. There will be no force acting on it. Okay, at least you can just try to separate it. So let's say this is the center, and then we can just draw a line, something like that. You can clearly see that, yeah, the force on the left side, on right side should be able to cancel each other perfectly. But it also tells you that in this direction, of course, there will be some force acting on this side and this side. They will also be able to cancel perfectly. Let's say for this side is shorter, but the distance between this side and this point is also shorter. So the force, this side will contribute a force pointing to this side. And then for this part, it will also attracting it. But yeah, even though this is longer, but the distance between this segment and the charge is also longer. So this side will contribute a force pointing to the bottom left. And this shell theorem tells you that these 2 forces will be perfectly cancel each other. So there will be no force acting on negative Q and also plus Q. Okay, because the both forces will be the same. So if one of it is 0, and the other one is also 0. Okay, this is shell theorem 2 tells you. Of course, you may not really accept the explanation here, but in chapter 23, when we learn about the Gauss law, then yeah, we will be able to talk about why this shell theorem 1, 2 are correct. Okay, so here's a quick checkpoint. It asks, figure shows two protons. Oh, this P is proton, this is proton, which means that it has a positive charge. And then, and one electron. So this is the negative charge. Okay, so on the central proton, what is the direction of the force due to the electron? Okay, so for A, what is the force due to the electron on the central proton? So on this one, on the central proton, what is the direction of the force due to the electron? Due to the electron. Okay, so this is a negative charge, this is a positive charge. So they should attract each other, which means that the force from the electron should point to the left side. Okay. And then, yeah, for B, the force due to other protons, due to other protons. Okay, so this is a proton, this is a proton. Both of them are positive charge, so they will repel each other, which means that the force acting on the central proton from the right proton, yeah, the force should also point to the left side. Okay, so the net force adding them together, so still pointing to the left side. Okay, so this is a easy checkpoint. Okay, so here we have a sample problem. Okay, so yeah, so here it says figure shows two positive charge particles fixed in place on an x-axis. Okay, the charge are Q1, Q2, and the particle separation R, capital R is 0.02 meter. What are the magnitude and the direction of the electrostatic force on particle 1 from particle 2? Okay, so this is very easy. Okay, so yeah, so F12 is nothing but K times absolute value of Q1, Q2 over R squared. Of course, you can still just keep all the signs of the Q1, Q2. Let's say here, Q is positive, Q1 is positive, Q2 is also positive. Just yeah, use what I mentioned before. Okay, this is the R axis for Q2, and this is the R axis for Q1, and then you just follow the vector form of the Coulomb's force, and then you can just find the force direction. Or maybe you can just need to calculate the magnitude of the force, and then you determine by your own understanding. Okay, so you see this is a positive charge, this is another positive charge. So the Coulomb's force should be repelling them. Okay, so you know F12 should point to the left side. Okay, so here F12 is this has this expression. So K is 8.99 times 10 to the 9th power, and then times Q1 is 1.6 times 10 to minus 19, and then times 3.2 times 10 to minus 19 all over. This should be capital R square. So we have a 0.02 square. Okay. So in between, you don't really need to write all the SI unit. You only need to write the SI unit for the answer only. Okay. So yeah. So this one should be 1.15 times 10 to minus 24 Newton. Okay. Force for the force, the SI unit should be Newton. Okay, so if we just write it in the vector form, so F12 is negative 1.15 times 10 to minus 24 Newton. Okay, so this is the x-axis. This is the x-axis. Okay, so for XYZ axis, YZ axis. I will use the notation I hat, J hat, K hat for the unit vector on x-axis, y-axis, and z-axis in this course. Okay, sometimes I will just write it I hat, or sometimes I will just write it I hat without a dot. Also for J, it can be J hat, or sometimes I just write it as a J hat without a dot. Okay, for the textbook, it shouldn't have the dot. It shouldn't have a dot. Okay, so yeah, for the K, we don't have this concept because K don't have a dot. Okay, and K hat. Okay, so this is for x-axis, this is for y-axis, this is for z-axis. Okay, so of course, x points to the right side. Okay, so I hat points to this side. So we have I hat here, and then with a negative sign. Okay, so this is the answer for question A. Question A. What is the magnitude and the direction? Okay, magnitude, direction is the or you can say this is the magnitude and then point to the left side, Yeah, but here I just write it as the vector form like this. So I just make this chance to tell you I hat, J hat, K hat are the unit vector of in XYZ axis. Okay, so far we have a F12 to be this expression, and then the second one is that if we place Q3 in between, which means that we have a Q3 also on the x-axis between Q1 and Q2. The separation between Q1 and Q3 are 3/4 of capital R. And then it asks you what are the electrostatic force. What are the net electrostatic force on particle 1 due to particle 2 and 3? Okay, so just now we already calculate F12 because here we have three particles. So only 2 force will act on Q1. One of it is from Q2, one of it is from Q3. From Q2 we already calculate, which is F12. So the remaining thing is to calculate F13. So and here we also know that Q1, Q3 are in opposite side. So the force F13 will attract them. So F13 will point to the right side. So here F13 equals K times absolute value of Q1 times absolute value of Q3 all over 3R over 4 and then square. Okay, so we can just plug in the number. K is 8.99 times 10 to the 9th power. And then times Q1 is this one, 1.6 times 10 to minus 19. And then times Q3 is absolute value of Q3 is 3.2 times 10 to minus 19. And then over 3 times 0.02 over 4, and then quantity squared. Okay, so in this case, this number is 2.05 times 10 to minus 24 Newton. Okay, so in vector form, F13 vector is 2.05 times 10 to the 24th power Newton. And then in positive x-axis, so I hat with a positive sign. Okay, so the net electrostatic force should be F12 plus F13. So F1 net should be F12 plus F13. Okay, which would be negative 1.15 times 10 to minus 24 plus N Newton I hat plus 2.05 times 10 to minus 24 Newton I hat. Okay, so both of it is on the x-axis, so we can just add the number together. So it becomes 9 times 10 to minus 25 Newton I hat. Okay, So it's point to the right side. Okay. Yeah. Okay, so next, here we talk about, we have another case. So here, rather than placing Q3, we place Q4 with an angle theta, which is 60 degree, So here we have a little bit problem. Okay, but anyway, Q3 is negative 3.2. Here Q4 has the same value, so we don't really need to Coulomb. Forgot the SI unit there. So anyway, we don't really need to calculate F14 again. So F14, is actually this one over 3/4 R quantity squared. Okay, so this value should be actually the same as 2.05 times 10 to negative 24 Newton. Yeah, we know we need to calculate again because distance and the charge amount are the same as Q3. So only the direction are different. Okay, so so here it also asks you the net electrostatic force. So here F14 should be 2.05 times 10 to minus 24 cosine of 60 degree and then Newton I hat and then plus 2.05 times 10 to minus 24 and then sine of 60 degree and then Newton J hat. Okay, so you just so this is F14, so you need to decompose it. This is F14 x-axis, and then this is F14 in the y-axis. F14 in the y-axis. So this is the one in the x-axis. This is the x-axis component. This is the y-axis component. Okay, so you can just calculate the number. And then finally, we can just add them together. So F1 net will be F12 plus F14. Okay, so the final answer will be negative 1.25 times 10 to minus 25 Newton I hat plus 1.78 times 10 to negative 24 Newton J hat. Okay, so this is the total force acting on Q1. Okay, so I think the calculation is not difficult. Only difficult thing is the vector summation. Vector summation will be a little bit you need to decompose it, but I don't think it is difficult. Okay, so here we have another sample problem. So let's try to finish this one and then we can finish the class today. Okay, so here it says, here figure shows two particles fixed in a place. Okay, a particle charge Q1, which is a plus AQ at the origin. So this is the first particle. And then the second particle, Q2. So this is Q2 with negative 2Q at x equals to L. So this is L. At what point other than infinitely far away can a proton be placed so that it is in equilibrium? The net force on it is 0. So its equilibrium point is stable or unstable. Okay. So so here we have several cases. So first, we should place the proton on the x-axis. If we just place it somewhere outside, just say if we just place the proton there, then you can clearly see that for the y-axis component, it can never be 0. So the first thing is that the proton should be on the x-axis. So in this case, on the x-axis, there are 3 segments. The first segment is on the left side. The second segment is in between. The third segment is on the right side. Okay, so we can consider one by one. Okay, so the first one is if we just place it in the middle. If we just place it in the middle, because Q1 is positive and then Q2 is negative, and then the proton is also positive. So which means that Q1 and the proton should repel each other, which means that F2 should point to the right side. And also, the proton is positive, Q2 is negative. So they should attract each other. So F1 and F2 should also point to the right side. So in that case, if F1 and F2 are not 0 and point to the right side, they can never cancel each other. So which means that we will discard this condition. Yeah, because the total force can never be 0. It asks you what is the equilibrium. Equilibrium point means no net force acting on the proton. Okay, so for the second case, which means that if we place the proton on the left side, so here Q1 and the proton are all positive, so they are repelling each other. So we can see that F1 points to the right side, and here the proton and the Q2 have opposite sign of charges, so they should attract each other. F2 point to the right side. So here the question is whether F1 can perfectly cancel F2. The answer is no, because you can see Q1 is plus AQ. A1 is plus AQ, plus AQ. Q2 is negative 2Q. And here the distance between them is large. Small. It's small. So the distance is small. The force should be sometimes like something like K times Q1, Q2 over R square. So for F1, Q2 for both, maybe I should make it like a Q1, Q2, because this is already small Q1, small Q2. Okay, so let's say this is Q1, this is Q2, and then this is Q2 for the other case. Okay, so Q1 for both cases are the same, and Q2 for this small Q1 is larger, and then the distance is smaller. So F1 must be large. F1 must be large. Okay, and then for F2, it is like K times Q1 Q2 prime over R prime square. Okay, so this R prime square is large, and then Q2 is small. F2 must be smaller than F1. So for this case, F1 and F2 can never cancel each other. So we also discussed this case. And then the remaining one is that we try to assume that the proton is placing on the right side, which means that this X should be larger than L. Okay. So let's directly go deep into here rather than quantitatively discussing about whether it can be one is large, one is small. So let's try to calculate it out directly. Okay, so here we have F1 point to the right side because this is positive, this is positive. Okay, so the force should be K times 8Q and then times QP. QP is the charge on the proton. And then here we assume that this is X. And we also know that this X should be larger than capital L, larger than or equal to at least. So this is x squared. Okay, and then it should have the same magnitude as F2. And F2 and F1 should point to the opposite side, and they should have the same magnitude. Okay, so here, K times, we only need to consider the absolute value. So this is 2Q, and then QP over. So this distance is x minus L. So this is x minus L quantity squared. Okay, so in that case, we can just do some cancellation. K and K will cancel. Q and Q will cancel. QP and QP will cancel. And then we can partially cancel 2 and 8 to be 4. Okay, so here we can just cross multiplication. So we have 4x squared minus 8xl plus 4l squared equals x squared. And then we can just move it to the left side. 3x squared minus 8xl plus 4l squared equals 0. Okay, so we have we should have two solutions. X equals 2/3 L and also 2L. But remember that we assume that the proton should be on the right side, which means that X should be larger than or equal to L. So we should discard this one. We should also discard this one. The only possible solution is X to be 2L. X to be 2L. So we have X to be 2L to be the final solution. And here it asks you whether the equilibrium point is stable or unstable. So far we'll not go deep into stability, because when you learn something like control theory, you will learn some complicated definition for stability of a system. But here it just tells you that whether the charge will hold at that point. It is like it's something means that if there are some force just acting on the force slightly, then the point will then the charge will just move away or just go back. Then it is called we'll just stay go away or go or stay that at that point. Okay, so here one student just asked a question. It just asked why Q1 and Q2 the distance is x is not L. Okay, so yes, x is not the distance between x1 and x2. X is the distance between Q1 and the proton. So the distance between Q1 and Q2 is still capital L. But here we just assume that the proton is placed on the right side, and then the x-axis coordinate of the proton is x. So x means from the Q1 to the proton. Okay, so on the left side, we just consider the force acting on the proton from Q1. So we should consider x squared to be the distance between Q1 and the proton. And on the right side, we consider the force acting on also the proton from Q2. So here, this distance should be x minus capital L. So we have x minus L quantity square there. Okay, so here, so let's move on. We talk about equilibrium stable or unstable. So it is just like if we have a curvature, if we just roll a ball there, if we try to push it to the left side, then it will just roll back and then just stay there. So this is so-called the stable situation. If the curvature is something like this, still you can place a ball there. You can place a ball there. Yeah, and then make it stable for just a moment. But if there are some force acting on it to the acting on it to the right side, then the ball will just roll away, and then it will not go back. Then it is called unstable. So how can we know whether it is stable or unstable? So we can just calculate that like this. So for the F net on the proton, it should be like K times 8 Q times QP over X squared. If it is perfectly X, if it is perfectly X, and then minus K, and then times 2Q QP over X minus L squared. So here we try to change. We already know that X should be 2L to be the equilibrium point. But if we try to change it to 2L plus delta X, we just try to move it a bit to the right side or to the left side, whether it will go back. So here it becomes K times 8Q times QP over X, 2L plus delta X, and then quantity square minus K times 2Q QP all over 2L minus L will be L plus delta X, and then square. Okay, like this. Okay, so we can just factor out something. We have 4K QP, and then we will have 2. We have a 4, and then over 2L plus delta X square minus 1 over L plus delta X square. Yeah, and then we can just expand it out. We just ignore this part because this is a positive thing. Okay, so here we have a 4 over 4L square plus 4L delta X plus delta X square, and then minus 1 over L square plus 2L delta X plus delta X quantity square. Okay, so we just move this 4 down. It becomes 1 over L square plus L delta X plus delta X square over 4, and then minus the same thing, L square plus 2L delta X plus delta X square. And here we already assume that delta X is small, so delta X square should be very, very small. And then when we try to compare whether this term is larger or this term is larger, we can just ignore this point. Okay, so here we have L delta X, and then we have here 2L delta X, which means that the denominator of the second term is larger. The second term, the denominator of the second term is larger, which means that this term is larger. This term is larger, which means that this expression should be positive. This expression should be positive, which means that for originally this is Q1, this is Q2, and then we place the proton here at 2L. If we try to move it to delta X, the force will be positive, which means that the force will further push it away. So which means that this is an unstable equilibrium point. Okay, so I think, yeah. Okay, so if you have questions, you can feel free to ask me, and otherwise, we will just end it here today. So I'll see you next week. See you on next Friday, Wednesday. Okay.